Hello everyone and welcome to this talk about large-scale real-time physical modeling sound synthesis. I would like to thank the SMC committee, in particular Andrea and Simone, for the opportunity of being here. It is really a great honor. And I would also like to thank my collaborators Craig Webb and Stefan Bilbao, who have contributed with a lot of videos and other content to these slides. So these are the people that I've been working with for a long time now, and credit goes to them too. So the title of this talk is a little bit of a statement, but it is my hope that by the end of it, you will be able to appreciate why I decided to use this title. So before talking about physical modeling, strictly speaking, it might be worth looking at some developments in the realm of digital sound synthesis. So I guess that a good starting point is the works by Max Matthews in the late 1950s at Bell Labs, where digital sound synthesis was pioneered, particularly wavetable synthesis. So in this case, Max Matthews recorded some geometrical shapes like triangles and squares and so on, and played them back at different rates to obtain a different pitch. He wasn't necessarily only interested in doing music, he was also interested in psychoacoustic phenomena and so on. But he made a lot of compositions, and one of the first such compositions is Silver Scale from 1957 that sounded like this. So that's pretty primordial, but I guess pretty good for the time. Of course, rumors about Max Matthews' research spread out to Europe very quickly, and a lot of people got interested into making experiments like that. So in particular, Jean-Claude Risset decides to fly out from France to Bell Labs in the late 1960s to pioneer another kind of synthesis that is called additive synthesis. So in this case, you sum up a bunch of basic building blocks, for example, oscillators, and you get more complex sounds by adding up, components that are much simpler than the result you get by summing them up. This is Computer Suite from Little Boy, 1968. So the sounds are pretty great in this case, but the problem with additive synthesis is that it's kind of expensive. You really need a lot of these basic building blocks to create a complex sound. And also it is kind of counterintuitive in some sense, because you need to specify a lot of parameters for each one of the building blocks. For example, the oscillators are specified by, decay time, amplitude, frequency, phase. So when you have like hundreds of them, can be pretty unwieldy to work with this kind of synthesis in certain scenarios. And that's the reason why researchers, develop more ideas in order to sort of simplify the process of creating complex sounds. And one of such ideas is modulation. Modulation comes mainly in two forms, amplitude and frequency. In the 1970s, John Channing experimented with frequency modulation. He patented his idea with Yamaha and established Karma at Stanford University. And the DX7 synthesizer is largely based on this patent that John Channing filed with Yamaha. So to do frequency modulation synthesis, you don't need hundreds of basic building blocks. You can work with just two, really, in its simplest form. But they're not equivalent, like in additive synthesis, where all the oscillators are summed up sequentially. Here what you do is that you use one of the building blocks to modulate the other, in this case in frequency. And the sounding output can become really complex that way. This is Turenas from 1972. So very interesting sound, a lot of textures, very brassy textures. You can hear a lot of vibrato going on. because John Channing was interested in that. And let's actually listen to what he has to say about his own discovery.
My musical training was the key to my discovery. It was not an engineering discovery or a mathematical discovery. It was altogether an ear discovery.
So John Channing says that frequency modulation was not a mathematical discovery, but an ear discovery. And this is a great link to physical modeling sound synthesis, I think. Because physical modeling sound synthesis has a specular approach, a mathematical model that informs and produces the sound. And the question is, why would you want to do that? There are a lot of answers that you could give in this case. But again, because we're taking a dive into history, let's go even backwards in time. Let's actually go back to the mid-18th century. And let's talk about what is today called the vibrating string controversy. In order to understand the controversy, let's make an example. The example of, for example, plucking an open string on a guitar. Well, there is nothing really complicated there. And of course, with modern technology, we're able to not only listen to the sound, but also to see it. So we can visualize the sound, for example, in the time domain. As you can see here, the axis says time. And what you see is some kind of vibratory motion that dies out over time. And that's pretty much that. But you can go a bit deeper into the analysis, and instead of plotting everything in the time domain, you can do it in the frequency domain. And what you see in that case is a bunch of peaks that are the overtones or partials of the sound. So one guitar note contains a lot of simpler tones that precisely we call the partials or the overtones or whatever you want to call them. So this is exactly the problem that the scientists faced in the mid-1800s. Well, 1700s, mid-18th century. But actually this problem was known even before then. For example, Marin Mersenne, about 100 years before the vibrating string controversy, was puzzled by the idea that he was, for example, observing a string and all he could see was some kind of repetitive motion at one frequency. But then if he actually focused on what he heard, then he was actually able to distinguish different overtones in the sound. So Marin Mersenne wasn't really able to reconcile what he saw with what he heard. So what he saw was this. This is great slow motion video that I got from the University of St Andrews in Scotland. So if you hammer a string, what you see is traveling wavefronts. So how come you hear different overtones there? What is the answer? Well, this is precisely what the vibrating string controversy was about. So D'Alembert, who plays the role of the mathematician in this controversy, formalizes the first ever example of a partial differential equation, which is in fact a musical problem, the problem of the vibrating string. So you could perhaps go back to the idea of why do we do physical modeling today? And one of the reasons is that perhaps it's always been that way. So ever since mathematicians started working with differential calculus, they were actually trying to solve a musical problem. So D'Alembert, formalizes the wave equation, and he also gives a solution in terms of traveling wavefronts, but not all kinds of wavefronts. He kind of excluded a family of wavefronts, and that's why Euler jumps in a year later. Euler was drawn equally by mathematics as he was by physics into this controversy. And he kind of, had an intuition that you should really allow special wavefronts to be solutions. For example, triangles. D'Alembert didn't like triangles because triangles have a discontinuous derivative, and that is not good if you're a mathematician. But because Euler was also a bit of a physicist, then he knew that when you pluck a string, for example, with your thumb, just before you release it, the string forms a triangle. And therefore he knew that because you can actually realize the shapes in practice, then they'd also better be solutions of the equation. But then there was another guy, Daniel Bernoulli, who jumped in a few years later, and he was actually driven by experimental investigation. And instead of giving a solution in terms of traveling wavefronts, he gave a solution in terms of the overtones, in terms of standing waves. And of course, D'Alembert and Euler weren't really happy about that because, they could see traveling wavefronts on a string. And and these scientists sort of argued for a long time and never really got to the end of the argument. Really, the person who settled the argument was Fourier, who was pretty diplomatic at that because he actually managed to reconcile everything into one beautiful theory, which is Fourier theory. And in Fourier theory, we know that we can actually represent a funny shape like a triangle that has a discontinuous derivative using standing waves that are perfectly well behaved like sine functions. Okay. And you can see that in the static case or in the dynamic case. So if you start summing up sine waves with appropriate amplitudes and frequencies, what you get is a traveling wavefront from a standing bank of sine functions. And you can add more and more of these, and you can get like traveling wavefronts that have very funny shapes, like in this case is a not-right wavefront that travels to the left and to the right and gets reflected at the boundary. And you can obtain that by summing up sine functions that are standing, which is pretty incredible if you think about it. But what is even more incredible is that you can go the other way around as well. So you can use traveling wavefronts to get a standing wave. So that's the beauty of Fourier theory. And that's why in the vibrating string controversy, Bernoulli, D'Alembert, and Euler were all right, but none of them was completely right. Fourier was completely right about everything. So the vibrating string controversy was instrumental in the development of early physical modeling techniques. And the reason is that if you now go back to the 1980s and we look at the early synthesis techniques, we see, for example, Julius Smith, that is the inventor of digital waveguides. Digital waveguides are essentially a discretization of D'Alembert's traveling wave solutions. But then you had other people at ERCAM, that is the center in Paris that was established by Jean-Claude Risset after he came back from Bell Labs in the 1970s. And here people experimented with modal synthesis, which is a kind of synthesis that is based on the idea that you can represent a system using overtones or modes. And of course, this led the way to more and more complex systems. So we're really getting closer to what we do today, and we're really getting closer to the idea of large-scale physical models. So here I have listed examples that were sort of too much for these early synthesis techniques. So you had dispersive systems or big systems like, two-dimensional, three-dimensional systems, interactive systems, where you have a bunch of subsystems that behave differently and they all interact together. And of course, you have nonlinearities that are really hard to treat and in fact impossible to treat with these early synthesis techniques. And this is the reason why, at some point in time, some researchers relaxed the idea of real-time synthesis to focus on behavior of musical instruments as physical systems. And one such people is Antoine Chen, another French person, that in the early 90s started working with mainstream numerical methods such as the finite difference method to solve equations that weren't really solvable with these early synthesis techniques. And of course, one person that majorly contributed to the idea of the use of finite difference schemes in sound synthesis is Stéphane Modal, who is one of the co-authors on this talk. Stéphane is the head of the acoustics and audio group, Brit School of Music in Edinburgh, and he was the principal investigator of the NEST project, and he wrote hundreds of papers that deal with the problem of the use of finite differences in sound synthesis. So the principle of operation of finite differences is essentially described by this animation by Stefan. So you discretize the differential operators that appear in the original equations, and you turn them into a bunch of algebraic operations that you do on a grid. And that way you're sort of able to update the solution to your model problem in time. Of course, things are much more difficult than what you see on this animation, but the principle of operation is pretty straightforward in this case. And this is also where I come in and Craig comes in, because we were both students in 2009 in Edinburgh with Stefan. Well, Stefan wasn't a student, he was the teacher on the course. But, we used to hang out in class and in restaurants, talking finite differences probably in this picture. So let's go see what actually we do for a living. So essentially, we're going to go and see how you can make use of Newtonian mechanics to make samosynthesis. And we're going to focus specifically on examples of linear versus nonlinear behavior. At the end of this showcase, I'm going to play demos of actual VSTs, actual plugins that you can go download from a website. And these are the actual real-time, large-scale models I talked about in my title. So the simplest object that is worth spending time on is the oscillator. This is an abstract concept, really, because there aren't really any systems in real life that behave like the harmonic oscillator. But you can at least approximate a lot of systems as if they were oscillators. So the oscillator is a useful idealization of something that never really is realized in practice, but that is close enough in some cases so that it is worth really spending time understanding this system. So you can realize an oscillator by attaching a mass to a spring, and that is usually how this system is described. And then if you do that and you use computers in order to see what is going on, you can again plot the motion in the time domain, and in that case you would see basically a sinusoid. But then you can use spectral analysis to see what is going on, and well, what you can see is just one single frequency component in the spectrum, which is the natural frequency of your oscillator. One thing that is important is the idea of energy conservation. You see that the oscillator possesses an energy that is made up of kinetic and potential, and we use this concept in modern physical modeling synthesis as a debug tool. So when we write code to solve complex physical models, energy conservation is really what we need to basically check that things are on track to become meaningful at the end, and we don't get bizarre behavior like solutions blowing up over time, and therefore your speakers blowing up perhaps. So the idea of energy conservation is really central to what we do, because it generalizes to nonlinear systems as well, as we would see in a second. Of course, oscillators come with losses, so energy decays over time for real physical systems, because sound does not go on forever, it dies out. So losses are important, but again, you only have one single frequency of oscillation even when you have losses. Things are slightly more interesting when you force your system, so you have an input forcing into the system. And in that case, you have two distinct behaviors going on. One behavior that follows the input sinusoidal forcing, and the other behavior that instead is just the same behavior as before, so the initial conditions essentially. So in this case, you have two frequencies of oscillation, because one frequency is the initial conditions, so the natural frequency of your oscillator, and the other frequency is the response to the input forcing. And these two behaviors are sort of independent in the sense that they go on independently of each other and they just sum up in the final output. But then things are interesting when you stretch out the oscillator a little bit too much, because in that case, you start observing behavior that is nonlinear, which is where the good stuff is. It's more difficult to do in practice, but it is also what gives physical model a sense of realism in a lot of cases. So if you stretch out the mass on the spring, the interesting fact is that the oscillator will still vibrate periodically. But now, if you look at the spectrum, you don't have one single frequency of vibration, but you have multiple frequencies. And they're all multiple of the fundamental, so that the motion is still periodic, but it is not one single frequency, it's a lot of frequencies. And again, if you look at what happens in terms of energy, you still have a sense of energy conservation, but in this case, you have an extra component, which is the purple one, that is the nonlinear energy component. And again, we make use of this idea of energy conservation in order to know that our simulation will eventually spit out a waveform that is meaningful in the sense that it will converge to the real thing if we have infinite sample rate. It is sort of, useful perhaps to visualize these same concepts in what we call the phase space. This is a diagram where you have displacement on the x-axis and velocity on the y-axis. And you can see the linear versus nonlinear cases are pretty different, because in the linear case, eventually the motion will end up on a circle, meaning that you reach the steady state of your system, and you will go on and on and on around that circle forever. But for nonlinear systems, things are not so straightforward, and the shape that is created in phase space is much more complicated. And there is still a sense of attractor, but these attractors are called strange in the sense that they do not really converge to something that is geometrically simple to understand, but it is still a little more complex. So in the second part of the talk, let's go see a couple of examples of real-time large-scale systems. The first one is a dynamic plate reverb, and plates are very interesting systems because they also present linear and nonlinear behavior according to how big the amplitude of the vibration is. But for the sake of reverberation, linear behavior is really what you're looking for. So, you can solve or try to approach the problem of artificial reverberation using the modal approach, which is, which resembles some kind of physical additive synthesis. So using the modal approach, you decompose the system onto a bank of oscillators, and then you add up the contribution of each one of these basic building blocks together. But the interesting fact is that now all the parameters of the oscillators are dictated by the physics of your problem. So this is additive synthesis, but it's physical in the sense that all the parameters will be set by the physics of the problem. So how many calculations are needed to solve the plate reverb? You need, in its basic form, at least 4 sums and multiplies times a number of modes, which ranges from 20,000 to 200,000, depending on size and material and whatnot. And you need to do that at the sample rate. So in this case, 44.1 kilohertz. So that's a lot of calculations, right? And it has to work well below real time. So obviously there is some kind of optimization that has to go into this algorithm. And the second example is derailleur, which is an interesting system where you have bars or strings that are connected together using these connections that are nonlinear. So in this case, the large scale is intended as the system is nonlinear. And you can see you input some signal into one of the bars or strings, and then the vibrations are passed around because of the nonlinear connections between all the bars. So here you've got your physical parameters for the bars and for the connections, and the bars can be strings sometimes. So that depends on basically what kind of excitation you want to use. Sometimes you can also use some pure signals like a sawtooth, but the system is also physical in the sense that the excitation can be a plucked string or a bowed string or a pitched bar. And then this excitation signal is passed through filter and a preamp stage and some effects. And all this driver system is then used to put the resonators into vibration. And these are the bars and the nonlinear springs. So this is what the system looks like. You have the driver view with all these different drivers and the EQ, low pass, filter, effects. And then you have the resonator view with the bars and the connections.